All right, so exam 2 is on Wednesday, next Wednesday. The topics are everything up through particle kinematics, including circular motion. So before I get on to new stuff that's not on the test, anybody have any questions about homework problems that are relevant to the test? Particle kinematics or circular motion? Yeah.
Should we do a 13 from 2D particle kinematics?
Yeah, I don't have that set with me. Do you have it? Okay, so 2D particle kinematics. Oh, by the way, in lab tomorrow we're going to do something. I'm going to try to sort of bring together some of the ways we've been thinking about stuff in lab and like the homework problems. So hopefully it'll sort of help you get ready for the lab exam and help you get ready for the regular exam. So to get the most out of it, if you have a chance, just be sure that you're sort of caught up on both of those two things, that you can make sense out of those things. Otherwise, it'll just sort of drift by you without it making a lot of sense, I think, tomorrow. But okay, number 13. So a small object moves around a circular path. And the object at the instant that we're thinking of is here. Or maybe that's actually, I guess that's just showing what this theta is. The radius of this circular path is 5 millimeters. The position in radians is negative 5t plus pi over 2. And we want to figure out first the angular velocity as a function of time, the angular acceleration as a function of time, the value of time when theta is equal to negative pi over 2. And something go wrong with that questions. Well, I assume, so it says at the instant from part C, draw the directions of, and then it's blank. So I guess you can choose what you draw the directions of. The idea is draw the directions of the velocity vector. And let's figure out the tangential acceleration vector, the centripetal acceleration vector, and it looks like we can do the total acceleration vector too. So let's do all of those. All right, well, this is theta as a function of time. And so to get from the angular position to the angular velocity, you just take the time derivative. So omega as a function of time is just the time derivative of the angular position. And so that's just negative 5. And the units are radians per second. So if the angular velocity is negative, which direction around the circle is it going, clockwise or counterclockwise? Clockwise, yep. And now that we have, yes? Nope, from position to velocity is a derivative, from velocity to acceleration is a derivative. It's only if you're going acceleration to velocity to position that it's integral. So okay, what's the angular acceleration? Well, this is a linear function, a constant function, so that's just 0. There's no angular acceleration. So right now, what do you think? Does that mean that there's no acceleration vector?
No.
It doesn't mean that. And the reason that there is acceleration is because it's not moving in a straight line. Even though we're going to see that it's moving with a constant speed, it's turning, and that means there has to be a centripetal acceleration. Okay. So C, what's the time when theta is equal to negative pi over 2? So we have this function, negative 5t plus pi over 2. So negative 5t plus pi over 2. And we want to find out when that's equal to negative pi over 2. And so you get negative 5t is equal to pi. So t is equal to pi over 5. And that's in seconds. Okay. And at that instant, so for part D, it says at the instant in C, we want to draw all these vectors. So we're talking about when the object is at this point here. That's when that angle theta is negative pi over 2. Everybody see that? Any questions about that? All right, and we already figured out that it's moving clockwise because the angular velocity is negative. There's no angular acceleration. So if it's going this way, the velocity vector is like this. What about the tangential acceleration? Is there? There is none because it's not changing speed. The rotation isn't changing speed. The centripetal acceleration is always right toward the center. So the centripetal acceleration is that way, and that's also the total acceleration. And now we could calculate these things. Might as well, since we're here. It doesn't say to do that. But the magnitude of the centripetal acceleration is omega squared times the radius of the circle. So that's negative 5 squared times 5 millimeters is 0.005. So that's 25. So I think you get 0.0125. Does that sound right? Are my decimals in the right spot? That's meters per second squared. We know that it's up, which depends on your coordinate system, but in our usual coordinate system, that's in the positive y direction. So the centripetal acceleration is equal to 0 positive 0.0125 meters per second squared. or you can just think of it as this way with a magnitude of 0.0125 meters per second squared. Okay. Any questions about that one? Any other homework questions you want to see? Yeah. It's cut off, yeah. I said draw the directions of the velocity, tangential acceleration, centripetal acceleration, and total acceleration. Yes. Sure. Okay, so you have a person that's capable of swimming 4.5 miles per hour. And what you have to recognize here is that that means the person can go 4.5 miles per hour compared to the water they're in. And this person swims across a river that's 0.15 miles across. And the river has a speed of 8 miles per hour. Okay, and the person's just going to swim straight across. The person's going to be aimed in the positive y direction, the way I have it here. Okay. And so the question is, how far down the river will the person, if the person just swims straight across, how far down the river will they be when they get to the other side? Well, we know that the velocity of the person relative to the ground is equal to the velocity of the person relative to the water plus the velocity of the water relative to the ground. The velocity of the person relative to the water is going to be in the positive y direction at, what did I say, 4.5 miles per hour. So 0, 4.5. And then the velocity of the water relative to the ground is this 8 miles per hour in the positive x direction. So this person's velocity vector is 8, 4.5 miles per hour. You could convert it to meters and seconds if you want, but I'm just going to do it in miles and hours. And now the question is, once the person has, achieved a distance in the y direction of 0.15 miles, how far have they gone in the x direction? So I'm going to put the origin here. You can think of this as a constant acceleration problem. It's actually zero acceleration, but it's zero constantly, so you can use those equations. So there's x and y. And I'll choose my time equals 0 to be when the swimmer leaves the shore. And time t is when the person reaches the other side. And now we can think about these values: t, acceleration, position at time 0, position at time t, velocity at time 0, and velocity at time t. We don't know t. We know that the acceleration is 0. We know that the initial position is 0. We know that the y position at time t is positive 0.15 miles. And we're trying to find the x position. And the initial velocity is 4.5 miles per hour, and we'll pretend we don't know anything about the velocity. Any questions about the setup? Okay, so the way we're going to do this then is we'll say py is equal to p0y plus v0y t plus 1/2 ay t squared. So that's 0 plus 4.5 t plus 0. And this py we know is 0.15. So p is equal to, I think that should be 0.03 repeating. We have time in hours. And now that we have that, the time that it takes to get across, we can plug that into the x equation that says px is equal to p0x plus v0xt plus 1/2 ax t squared. So we have 0 plus 8 times 0.03 repeating plus 0, and that answer is 0.2 8 times, what's that, 22.26 repeating? Is that right? And this is in miles, so like a little over is that right? Can someone calculate that? What's 8 times 0.083 repeating? Okay, great, thanks. So a little more than a 1/4 mile downstream. Any questions about that? Any others you'd like to see? Yes. Okay. That one I have. Okay, so this is circular motion. So you have a bicycle And I'm just going to draw the wheel. It talks about like the speed and stuff that this bicycle is moving. But the bicycle, the body of the bicycle is moving with the center. You know, like the frame attaches to the wheel at the axle. And so we can, talking about the speed of the vehicle itself, we can always just think of that as the center. Okay. And what do we know? We know that it's moving with a constant speed. Let's say it's going this way, of 8.80 meters per second, so like 20 miles an hour. And it has a radius of 0.34 meters. And we want to calculate, so if I call this C and the bottom B and the top T, we want to calculate the velocity at the top, the velocity at the bottom, and then C and D, we want to calculate the acceleration of the top, the acceleration of the bottom, and then the last question, E, is once you calculate the velocities, why not just take the time derivatives to get the acceleration? Okay, well, the coordinate system we're going to use always has, for rolling without slipping, always has the y-axis pointing straight out of the surface. So the y-axis is going to point straight up for this one. The x-axis is this way. For the velocity of the center, so the rolling without slipping equation says that the velocity of the center as a vector is equal to negative omega r and then 0 for y. And we're given what this is. It's positive 8.80. So now we have two equations. We know that the radius is 0.34. The x equation says negative 0.34 omega is equal to 8.8. And so omega is 8.8 divided by 0.34. Can someone calculate that for me? .88, and there's a negative sign, radians per second. Okay, so which way is it rolling? Which way is it rotating? Clockwise or counterclockwise? Clockwise because it's negative. And now look at the problem. Does it make sense that if the wheel is moving that direction, that it has to be rotating clockwise? Yeah, that makes sense with your intuition. But it didn't ask, well, so why did we do this? It didn't ask for the angular velocity, but in order to calculate the velocity vector of the top point or the bottom point, any point on the wheel, we're going to use relative motion, and we're going to have to know that angular velocity. So now that we have this, we can say that the velocity of the top relative to the ground is equal to the velocity of the top relative to the center plus the velocity of the center relative to the ground. This one we know, that's just this. And the velocity of anything relative to the center, you can just get using circular motion. Okay, so now let's think about the velocity of the top relative to the center. So what we're talking about is a circular motion where this thing is moving with a clockwise angular velocity of 25.88. And the radius is 0.34. What's the direction of the velocity of the top, assuming that the center is still? Positive x direction. Anybody have any questions about that? Does that make sense? And to get the magnitude, that's equal to the absolute value of omega times r, which is 25.88 times 0.34, which is 8.80. This is meters per second. Well, we know the direction is in the positive x. We know the magnitude is 8.8. So put those two together and you get a velocity vector of the top relative to the center. That's 8.800. And now we just have to put that into the relative motion equation. So the velocity of the top relative to the ground is equal to the velocity of the top relative to the center plus the velocity of the center relative to the ground. We just calculated that top relative to center is 8.80. We were given that the velocity of the center relative to the ground is also positive 8.80. And so the velocity of the top relative to the ground is positive 17.60. So in rolling problems, the top of the wheel, the point that's instantaneously at the top of the wheel is always going in the same direction as the center and twice as fast. But you should be able to do that calculation. Okay. Any questions about that? Yeah.
So if we had a question like this, would you want us to do all the work?
Yeah, I would want you to, yep. And then, so let's do it for the bottom now. It's the same idea. So the velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. This is the one that's given. This is circular motion. And so to calculate the velocity of the bottom relative to the ground, we'll think about this circular motion again. There's the center. Here's the bottom. We know that this wheel is rotating clockwise at 25.88 radians per second. So now, assuming that the center is fixed, which direction would that point be going? Left or right? Left, yep. So it's like this. The magnitude is going to come out the same as it did for the other one, for the top point. That's going to be absolute value of omega is negative 25.88 times 0.34. So we get a magnitude of 8.8 meters per second. But this time, that velocity is in the opposite direction. So the velocity of the bottom relative to the center, it's in the negative x direction. So this is negative 8.80. For the top, the velocity of the top relative to the center was positive 8.80. And so now when we go back to the relative motion equation, it says velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. We get negative 8.80 plus positive 8.80. This time those cancel, and you get that the point at the bottom is at rest at that instant that it's in contact with the ground. It has no velocity. So it's slow as it comes toward the ground. It slows down, is exactly at rest as it touches the ground, and then starts to speed up as it goes away. Okay. And you can think of that as a requirement for it not to slip, because if it had a horizontal velocity when it was touching the ground, you can think of that as the definition of something slipping. You know? Yep, it is always the case. But you need to be able to do these relative motion equations. So, yeah, that's right. That's right. Because it's important to get used to thinking of things in terms of this relative motion. It's going to be a really useful thing later in the class, but even more as you go on into other engineering classes. Okay, so let's calculate the acceleration. And let's just do it for one of these 2 points. So part C, let's calculate the acceleration of the top, okay? So the acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center. You know, you should notice this is all starting to be sort of redundant. We're using velocity and acceleration. We're talking about different points, but the approach is just the same for all of these things. Acceleration of the top relative to the center plus acceleration of the center relative to the ground. What do we know about the acceleration of the center relative to the ground in this problem? Yeah, so it's moving with a constant speed. So this is 0. We're talking about the acceleration of the center. So if this thing's moving with a constant speed, the center is just moving with a constant speed along the ground, you know, 1 radius above the ground. And so there's no acceleration. You could also think of it in terms of, you know, use the rolling without slipping equation that says the acceleration of the center is equal to negative alpha r 0. Well, alpha is 0, so this goes away. In this problem, if there was an alpha, then the acceleration of the center would be something. So now we just have to calculate the acceleration of the top relative to the center. And that's a circular motion problem. So here's the center, here's the top. We know that it's moving clockwise at 25.88 radians per second. So the velocity is this way. Is there a tangential acceleration? No. Centripetal always goes toward the center. So centripetal acceleration is down. That's also going to be our total acceleration. The magnitude of the centripetal acceleration is omega squared r. So that's 25.88 squared times 0.34. And what do you get for that? 227.72 meters per second squared. That's the magnitude. And we know the direction is in the negative y. So as a vector, the centripetal acceleration, which is also the acceleration, the total acceleration in this case of t relative to the center, is 0, negative 227.72. And now put the relative motion equation back together. The acceleration of t relative to the ground is equal to 0, negative 227.72 plus 0. So 0, negative 227.72 meters per second squared. Any questions about that approach? Yeah, that's a great question. I think, well, I would definitely, when you know that it's going to be a relative motion equation, a relative motion problem, I would write that up at the top. So you know what parts, like figure out what relative motion parts you need to calculate, and get that up at right at the start when you recognize it. And then I would just, I think this is a good way to do it. I mean, just label the pieces that you're calculating. So you have the relative motion equation here. We figured out in this problem, we were sort of already given the acceleration and velocity of the center relative to the ground. So then we know we only have one more piece to do. Be clear to yourself about where the work is for that piece that you're calculating. So all of this has this one heading, you know what I mean? So you don't get confused about what you're calculating. And then after you're done with that, you can go back and put it back into the relative motion. I think that makes sense. I mean, that's the way I do it. So of course I think it makes sense, but okay. Any other questions? How about any other homework questions? We only have 10 minutes left, so I don't think I'm going to go into any new stuff. Anybody want to see any more of these or want me to make up a new one or? Oh, okay. Yes, thank you. So part E said, okay, so we got a velocity vector. So let's say for the top, we calculated that the velocity vector of that top point is equal to positive 17.600, okay? And the question is sort of, why isn't the acceleration of the top, okay, so why the acceleration of the top not equal to the time derivative of this velocity, which would just say that the acceleration of that top point is 0, 0. You know, why doesn't this work? And the answer is, and this is something that you always have to keep in mind with these derivative relationships, the derivative relationships only work if you have your position or velocity or acceleration given as functions of time, okay? What we did here was we calculated that velocity of the top point at a single instant, and you can't take a derivative of a single instant, you know? So basically, what that's doing is if you have a function like this, okay, and you calculate that the height of this position is here, you know, what's the value there? Let's say it's 4, right, at a single instant. Just based on that one constant value, you can't take the derivative of that function, think of that function as 4, and assume that it's horizontal here, okay? You have to know what's happening before and after that point in order to come up with a slope for it, okay? So that's the thing. So anytime you're thinking about using derivative relationships, you need to be sure that what you have is a function and not just a point, okay? Any other questions? Okay, let's stop there, and tomorrow I'll have some problems that'll hopefully help bring this stuff together.